Today, Mr. Maiano moved his religion test to Monday, and so basically, I don't know if you guys all have him or not, it doesn't really matter, but there are a couple people who do, and so that conflicts with them taking a test. So the juniors will take it on Tuesday. We're just going to make that rule. Juniors are going to take the test on Tuesday, sophomores are going to take it on Monday. It just makes it easier for everybody. Especially since like all of the juniors in my IBEL have already had 2 tests on Monday, so it's just blanket rule. Okay, so we're going to keep reviewing. On Monday, since so many of you won't be taking it, I can't send you all to the library. I'm going to have you do a quiet study hall in here. You're going to have to be quiet so that everyone else can take the test. Okay, so yesterday we talked about atomic radius. That was what 8.6 was on. Always keep in mind too that whatever I put up here is kind of like the bare bones review. If there's other stuff that we talked about, that's also testable.
There's a lot more juniors and sophomores. Why is the sophomores study hall? Like,
Not everybody has study hall.
no, I know, but you can't send them to the library anymore. You have to send them to whatever teacher.
Oh, I don't know if I want to put that many sophomores in the study hall, but I mean I can figure it out. It's actually a good idea. I'll look at who has study hall right now.
Can you move more towards the board so they can see you?
What? Oh, that? Great.
Yeah.
I don't
You
see
should
it.
stand just
I don't
out of
see it in
frame.
one place, so that's not going to work.
Well, just
Okay.
like
I have another.
Stop. It's not important. Not important. Not important. Up here. This is important. Okay. So, first thing we did at 8.7 was we did the electron configurations of the ions. So any main group, you just remove or add based on the last energy orbital that was filled. So if you're making sodium plus, sodium is 1s2, 2s2, 2p6, 3s1. If you make sodium plus, it loses its last electron. That's the electron configuration for Na plus, right? So you remove or add in the last orbital that was added to. If it's, and this was something that a lot of people made mistakes on that one homework assignment. If it's a transition element, it's gonna remove from the highest principal quantum number orbital first. So for example, in the middle, it's gonna lose the 4s electrons before it loses the 3d, even though the 3d are listed last and they're added to last. So make sure you know that. So if you're doing an ion here in the middle, you gotta take out those s electrons before you touch any of the d electrons.
And it's just because that they're further away.
Yeah, that d orbital gets more and more stable as you add electrons to it. What's up?
If like the 4s went to 0, would you keep it there or just completely?
You just don't write it anymore.
Go on.
Yeah. And then after you take them out of the 4s, then you can start taking them out of the d. If you need to. Okay. These are true statements, obviously, but you also need to be able to explain them. So cations are smaller than their corresponding neutral atom. So Na plus is smaller than Na. That should make sense. You're especially for almost all of the cations that exist normally that we talk about, you're taking an electron out of that last orbital. Once you make Na plus, you don't have any electrons in the 3s orbital now. And a 2p orbital is smaller than a 3s. Also, there's a smaller number of electrons than protons at that point, so they're sucked in nice and tightly, and the cation is smaller than the neutral atom. What's up?
Or like something like a halogen, like chlorine or something like that. Would the anion still be bigger because like when you're adding the electron, you're making it like a noble gas. So, but wouldn't it be like smaller almost because I thought with like the 8 electrons, like it's more stable, so it kind of like isn't as big. I don't know.
It is more stable technically. That doesn't mean that it has to be smaller. So in this one, F minus is bigger. That's your anion. Because you've got an extra electron here, but no more protons, so there's a little more interference with those last electrons. It's not a huge change, but enough so that they're repelling each other enough so that it makes the anion a little bit bigger. They push outwards a little farther.
So basically, if you have more electrons over there.
Right. Which is exactly what that says.
Okay.
Just in different words. Okay. All right. And then for the ionization energy goes down a column, increases across a row. The reasons for that are the same reasons we had for atomic radius. Down a column, the electrons are farther away, so they're easier to pick off. So the ionization energy is lower. Across a row, the effective nuclear charge goes up, they're sucked in closer to the nucleus, so they're harder to pick off. So the reasons are exactly the same as for size. You just a different application of them.
When you say across the row, you mean like that way?
Left to
Can
right.
you repeat that again? Why is it the same?
Because, so the reason that down a column they get bigger is because they're bigger, or they're filling bigger orbitals, right? So filling bigger orbitals means the electrons are farther away from the nucleus, so they're easier to pull off. They're not as close to the positive charge of the nucleus. And then across a row, they're smaller because the effective nuclear charge goes up. Well, because of that, those electrons are close to the nucleus, they're sucked in tightly, and so they're harder to pull off. You have to put in more energy to pull off an electron. Remember that this ionization energy is the energy required to remove an electron. How much energy do you have to put in to remove an electron? So lower ionization energy means it's easy to take off an electron. Amy, what's up?
Nothing.
Okay. Sorry.
What is the 2A?
That's what I was going to do. That 2A to 3A and the 5A to 6A is your, those are your exceptions. That's what I'm looking for. So, instead of ionization energy increasing consistently all the way across the main group, it actually goes up and then it goes down a little bit at the 3A and then keeps going up and goes down a little bit at the 6A again and then keeps going up. So there are two blips where it goes down instead of going up. So let's look at why. Here's beryllium. I'm trying to think of what I want to do. Why can't I think? Oh, okay, beryllium. 2s2. And here is boron. And then, okay, so this is the second.
What if it's plus 1?
What? Did I do or two? I'm sorry. Yeah. This is the second row going left to right. My talk about it is left to right across that row.
2P1.
Okay. So, what?
It's 2P1, right?
Yeah. I don't know. I'm running quickly. So, lithium. From lithium to beryllium, the ionization energy increases because those electrons are sucked in. If we were to follow the pattern, borons should be a little bit higher too. But this electron, this one electron that we're talking about removing, is actually easier to remove than that electron because the 2p, it doesn't get as close to the nucleus. It's not penetrating into the 1s as much, so they're a little bit easier to pull off. They don't spend as much time close to the nucleus. So, and that's true all the way down the 3a column when you're comparing it to a 2a. That extra p1 electron is a little bit easier to pull off than this S2 electron would be. So the ionization energy goes down a little bit when you hit the 3A column, and then starts going up again after that. When you go 5A to 6A, so nitrogen to oxygen, 2s, 2s, nitrogen, 2p, 3. If we were following the trend, oxygen's ionization energy should be higher than nitrogen's, but it's not. And again, we're talking about first ionization energy, so only taking off one electron. Because this electron is doubled up, it's close to another negatively charged electron, which it doesn't like. This electron is actually easier to remove than that one because you started doubling up. And that's true all the way down the 6A column. So instead of this ionization energy being higher, it's actually a tiny bit lower. And then it starts going up again after that. Okay, so goes up, then it goes a little bit down, then up, and a little bit down, and then up again. What's up?
With carbon has
Yup.
2 in the 2p.
Uh-huh.
Does carbon also have a lower first ionization energy than beryllium?
Then beryllium?
Yeah. Like this is beryllium and then the boron it goes
Oh,
down
no,
a
no, no.
bit.
No, I can,
Or is carbon still higher than?
carbon should still be higher. Here's beryllium, boron, carbon. Carbon, nitrogen, oxygen, fluorine, neon. Okay, so carbon is actually, this is beryllium right here, and that's carbon. So the jump from boron to carbon overtakes that little tiny blip that was there. Okay? Does that answer your question? Okay. All right, cool. Yeah.
Test, if you ask us about like the trend in atomic radius,
Uh-huh.
we say that when you're moving from left to right, nuclear charge, the effective nuclear charge gets higher, which is why electrons are floating closer. Do you want us to explain why?
Yes.
Like, why is the effect of nuclear? It's because there's no protons.
Right. More protons and the number of shielding electrons doesn't go up. That's what we spent a long time talking about
When you
yesterday.
move down, the effective nuclear charge doesn't get bigger because
It doesn't change at all, it's just it's got bigger orbitals.
the effective nuclear charge doesn't go up.
Right, and more just because bigger quantum numbers means bigger orbital. It's just the only difference is size. But yeah, it has to do with the effective nuclear charge, so it's not changing at all.
I have a question.
Okay. All right. Blah, blah, blah. Oh, and you should also be able to predict where that jump in ionization energy occurs. So remember we said there's a first ionization energy to take off the first electron and a second to take off the second electron, yada, yada, yada. So lithium's going to have a first ionization energy. Well, actually, let's do sodium. Sodium's going to have a first ionization energy. When you take off that one electron, now it's like a noble gas. Its second ionization energy is going to be way, way, way higher than its first ionization energy because it doesn't want to lose another electron after it's like a noble gas. So for all of the first column, there's going to be a jump between the first ionization and the second ionization energy. What, Danielle?
Then anytime they have, so eventually they get 10 electrons.
Well, it's not 10 electrons. Like,
That, what would it be in like?
it's 8 valence electrons.
How do we?
It's when they become like a noble gas. So calcium loses 1, then it loses 2. After its second ionization energy, you're going to have a huge jump before
Should
the
we just
third.
like count that?
Yeah, that's the easiest way to do it.
The out of comes
So first ionization energy, losing 1 electron, right?
in. Yeah.
So I put energy into sodium, it's lost 1 electron, and now it's like neon, right? Because it's lost an electron and it now has 10 electrons like neon does. Okay, 10 electrons is very stable. They all want to be like noble gases, right?
I thought it was 8. It's 8 valence.
8 valence electrons,
Oh.
10 in this case because neon has 10. So being like a noble gas is very stable. So if I want to put in more energy to remove a second electron, it's called its second ionization energy, I'm trying to make it not be like a noble gas anymore. So that's going to have to take a lot of energy because it wants to be, that's stable. So the second ionization energy is going to be huge in comparison to the first one. Okay, next section. Okay, electron affinity. So ionization energy is removing an electron. Electron affinity is energy to gain an electron or put an electron on an element, to make an anion. Down a column, they don't really have any recognizable trends except for 1A, the alkalis, they get more positive. This gets weird because we're dealing with mostly negative numbers, so we don't talk about bigger or smaller, we talk about more or less negative.
What is affinity?
What?
What is the EA electron affinity?
The energy required to add an electron to an element.
So ionization energy is the energy to remove
Right.
the electron.
And electron affinity is to gain an electron. Okay. So, that's generally true except for 2 of basically the same locations. So you would expect it to become more negative left to right, except at 2A and 5A. Again, there's one of those blips in the graph. Here's your 2A element, right here, beryllium. The reason it's harder, that number is less negative, so it's harder to put an electron on, because you have to start a whole new orbital. You have to start a 2p orbital, and it doesn't want to do that. 2p is higher in energy. So beryllium's electron affinity is less, well, this one's actually positive, but the 2A electron affinity is less negative than 1A.
And by less negative, that means
Harder. The more negative it is, that means it's releasing a lot of energy. It wants to be at low energy, so releasing a lot of energy means it's stable. What's up?
2 questions. Is 2A also getting more negative? It looks like it is.
What do you mean?
Like it goes from 0 to 0, -2 to -5.
Oh, you're talking about down?
Yeah.
Yeah, but that's not really, I mean, we don't really talk about that as a general trend, since they're all very close to 0 or very close to being positive. We talk more about left to right for electron
And
affinity.
wait, I just have
What's
a
your other
question. Why are some of them 0, like random?
It's not 0, that's greater than 0. That means they're just positive numbers. That means that you actually, for beryllium and only a couple others, you actually have to put energy in to add an electron.
Okay.
Amory?
Would 3A be another exception because it gets less negative from 1A?
But it gets more negative from 2A. It's in comparison to the one right before.
Okay.
So it should go more negative. This one goes up, but then it goes down, down, up, down, down.
Okay.
Okay. Leanne?
Is electron affinity where it was, like, you know, we were working on, like, the positive, like, jumps and stuff like that. Is that ionization energy? And then, like,
Yes.
it's negative for electron affinity?
Yes.
Electron, okay.
Yes. Jay? What's your question?
So that EA is going to be more negative.
Going left to right, right.
So that means you will need less energy.
You don't have to put energy in at all. It releases energy. A negative energy means it's releasing energy when you put an electron on. Right? So if beryllium's, well, that's a bad example.
So does that mean it
So
releases?
so let me lose my thought. I'm trying to look for actual numbers for you here. Borons is -27, lithium's is -60. Okay. Let's give you some numbers. Kilojoules per mole, kilojoules per mole. That means it's releasing 60 kilojoules per mole when you add an electron to it. Remember that everything wants to be at lower potential energy, right? So the more energy it releases, the less it has in and of itself, so it's happier. That means this guy wanted that electron more than this one, so he released 60 kilojoules per mole.
Yeah, can you repeat the Y2A exception?
Because to add another electron to 2A, you'd have to start a new orbital. And that's higher energy, right? If I put another electron in here, I have to start the 2p orbital, okay?
So is lithium more positive than boron?
It is, but again, it's compared to the one right before it. This is a blip, so it actually becomes positive there, but after that it goes more negative. So boron's more negative than beryllium is. And then carbon's more negative than boron is.
So like thinking of like more negatives, like it's the lower, like the negative thing, it's more negative because it has more electrons? Because like, I mean, like normally like you would think -60 is like
Better.
more negative than -27.
It is, but again, I'm not comparing boron, like the trend isn't boron to lithium. I'm comparing it to the
I
one
know.
right before it.
Yeah, so like if, so what's carbon's thing? Like, 'cause-
Carbon is
-122.
-122.
so is carbon more negative?
Yes. Carbon, when you get down to carbon, it's -122 kilojoules.
But I thought you said that it would be more positive.
No. It becomes more negative across the row.
Oh, okay.
Okay?
Are there any exceptions to that that are becoming more negative?
Yes.
Besides
That one that I just talked about, and I was going to do the 5A one as well. So this is your 2A exception. 5A is right here, nitrogen. 5A, 5A electron affinities are more positive or less negative than 4A, because that's where you have to start doubling up an electron. It really doesn't want to double it up, so their electron affinity is a little bit less negative than.
So does that mean it doesn't want to double up
Correct.
an electron, so that means that it
Releases less energy when you put that
Releases
electron.
less energy.
Yes, these negative numbers are actually hard to think about. What's up?
Okay, so, okay, so the reason that the 2A does it is because it doesn't want to put the other electron in the,
Oh, it doesn't want to start a new
it
orbital.
doesn't want to start a new orbital,
Right.
because then you have to go to the p orbital,
Right.
it doesn't want to do that.
Right.
And then the reason that the 5A does it is because you have to start doubling up,
Right.
and.
That means the electrons are close, electrons repel. They don't want
Right,
to be
they don't want to
near
be next to each other.
Right.
But it's the opposite for ionization energy.
each other. Right.
They're easier to pick off when they.
Right.
Okay.
Exactly.
Okay, got it.
Okay, and then we have metallic character, which makes a little bit more sense. So down and left, more metallic, up and right, less metallic. Because of all of the other things we talked about. Metals lose electrons easily. All of the things with lower ionization energy are to the left and down, so those are more metallic. Non-metals gain electrons. The ones with the most negative electron affinity are up and to the right. So all the non-metals are up and to the right. What's up?
When we get into our homework, sometimes it would like be up one and like to the left. Like say if it was
So say
down and to the right. would they-
right. That's normally those ones that you can't make a conclusion.
Can't
So
make, okay.
right, yeah. If I did atomic radii down to the right, so phosphorus, selenium, you can't do because this is bigger with that smaller.
But if it was down to the left.
Bigger. So germanium would be bigger than phosphorus.
So probably-
Okay. All right, let's look at a couple of these types of problems. I'm going to have you do like 3 at a time. Do these 3 things. So this is the kind of thing that's still conceptual but doesn't require you to explain things. It's just show me that you understand what the trends are.
All this photo shows my point that, bromate electrons and negatives.
What do you made electrons?
Remember, like,
Well, God did.
made the concept of, like, the negativeness in physics.
Did you guys Mr. House?
I didn't.
No, okay. No complaint.
No, I hear it. Makes me sad.
Yeah, because negatives are made up really. There's like no really negative.
Right, that's what I was trying to
That's not
explain.
my- no,
That
that's
doesn't
not my
actually,
point.
isn't a thing.
That's not my point. No, you're missing the point.
Yeah,
There's
actually nothing negative in like how are the
No,
electrons
that's my
negative?
point.
That's like
Right.
just like
You
an
don't
opposite.
even know what I'm talking about, right?
Right, there's not a, negative isn't a thing. It's just
Yeah,
when
I
you've
know.
assigned this thing is called
Yeah, they
negative.
assigned it
But
wrong.
there's like ionizations and stuff like that. So I
the
mean,
point.
I know, I didn't make it up. I
You
didn't do
shouldn't
it.
be
I
adding-
didn't. I'm just
The
saying.
thing that actually exists shouldn't be the negative that's moving, like, shouldn't be negative.
An electron isn't a negative thing. It has a negative charge. But the electron, you can't call it negative. It just has a negative charge on it. That's different.
Yeah, that's what I meant.
Okay, that's different. Okay, do these problems and shut up.
I'm just saying, they should have called it something different. Or at least.
Well, it would have been like the same thing, I guess.
It's actually relevant.
Should have signed it
That's
wrong.
what you're talking about nonsense.
Signed it wrong.
When do we go back to the math and the
Yeah.
Probably not so
that
much.
people can understand?
Yay!
Not so much.
We never do that.
Thank God.
No.
Not so much.
That's
No,
fine.
I don't
How to be in this class. I don't get to go to shop.
There's not really that much. Like, there's not much left in the book that has a lot of math in it. Most of it's cool and just learning stuff. There's a little bit, but not as intense as this has been before. There's a lot more.
Decreasing, there's so many.
So our final exam will be more conceptual based than math based.
That sucks.
I failed on
So it'll
that.
be a lot more
Yours-
short answer than multiple choice.
Danielle,
I don't understand mine. I can ask you conceptual questions and multiple choice.
Yeah, I think you should do that.
I like it better when you explain it because then you can prove you know more instead of just getting one answer.
No, okay.
I think we should get bonus
Atomic
points if we
radius
know more than
decreases.
other people.
Right. Decreases right
Maybe
now.
not electron configuration.
So decreases, right?
Right, and up, right.
So
It's bigger going down. Right.
I love.
So when it says in decreasing electron phase, it means bigger first.
I-
Yes.
I talked to
Big,
myself.
small.
Big,
You do
like,
talk to yourself.
bigger,
Small.
smaller. Bigger,
I
smaller.
bet.
Yes, bigger, small.
Oh, okay.
He was doing smaller, smaller, which is also true.
See, Sharpies
It's
are
like
really
almost
good.
right now,
It's
it's
also
just
streaky.
Stop.
And
Stop.
these are streaky because they're paper made brown. Yes, make you look like that.
No, what's wrong with that? Still-
Great.
Well, it doesn't just
Get
disappear.
back to the next slide. Okay.
I think your hair looks nice.
Thank you.
Where's Selenia?
So these are actually really good multiple choice because I can put 4 different orders on the multiple choice.
You should do like 20,000.
There's actually only 16 possible combinations.
Where is PE?
No,
Okay,
I
wait,
mean like
can I
20,000
so the
questions.
pattern
There you
for,
go.
You don't even know what the pattern is.
You didn't say that.
C.
Why don't you both do it?
C what?
but decrease
That's
down.
all C.
Yes.
But I could find
Why are you looking for C?
But those are all in the same row.
Are you kidding?
What, Jay?
for the test, is it only gonna be from 8.6
To
to
the end.
yeah, it's not gonna
Right.
you're not gonna do the first half.
No, but that'll show up on the final.
Yeah, but
Well, yeah, but there's also the ability to write electron configurations for like the ions and stuff. That's from the first part of the chapter. But I'm not gonna do, I'm not gonna like hit the stuff hard that was in the first half. What?
Is the second half of that thermochemistry chapter going to be on the final?
Yeah.
So there's going to be some math.
Where's the
Wait, what math?
I think the exam
The second
should
half of
be
the thermal
write an
chapter that we
essay
did.
about what if you like chemistry?
Transition metals, when they lose 3 electrons, they lose from the highest.
No.
It was S first, then D.
I did.
I hate when that happens.
Okay.
Oh, this is like difficult.
Make sure to, because the other thing I would do is just have the right answer but have it flipped around. Make sure you know what I mean by decreasing, increasing. Decreasing is biggest to smallest. So effective nuclear charge goes up left to right, which is why the radius gets smaller. So something over here is going to have a bigger effective nuclear charge than something on the left side. So in decreasing order, this should be S, S-I-A-L-M-G.
Yeah.
S, S-I-A-L, M-G.
That's what I got.
Decreasing order.
I did the opposite.
So,
Are these actually just numbers?
Hey, no, what?
I'm talking.
Hey,
yes.
I can.
We have a quick question.
What?
And then you move across.
oh my god, I'm scared.
Guys. The rest of you should not be talking.
Since it's losing 3, but it loses from the S first.
It'll lose 1 d electron.
Okay.
Yes. Okay. Decreasing atomic radius. So bigger down, bigger to the left, smaller right, smaller up. Okay. So we've got cesium is over here, and antimony, and sulfur, and lead is somewhere on this.
Underneath.
Wait, you said you get
Yes.
it gets bigger as you go down,
Bigger down. Yeah.
But
The orbitals are bigger.
and then to the
And smaller to the right.
Wait, how is it again?
God.
You get it.
Okay.
So true.
What do you mean after?
There's your order for that one.
So we do.
Guys, I don't know if this helps you or not, but so like when I did this in high school, we'd have like our stupid little, here's my periodic table.
Where'd you go to high school?
Michigan. So here's an atomic radius periodic table.
They look different.
Bigger. Bigger. What you asking?
I was saying, did it look different when you were in school?
What
No,
is
it's like the
Like
United
the
States.
table.
A little bit. Yeah, they just discovered one. But that's a general idea. Bigger, bigger. That way. Smaller. Smaller. So we drew little diagrams like this to kind of help us get the idea of what the direction is. And 7-1 for ionization energy and for electron affinity, something like that. So that kind of helped me get the idea. 1 second. So that way when you're looking at a problem like this, I'm just finding the 5 on the board, or on the periodic table. Here's one here, and we're going upright, and then up. So I look at them all 5 as a pattern. Don't try to do them each individually, that takes too long. I mean, if that's the only way you can do it, fine. But sometimes looking at them all, they're going to follow a general pattern. You can see what order they should go in. What's your question, Danielle?
Is that the same for all of them?
No, ionization energy is gonna go,
Can you do that chart? Does that actually help?
yeah,
Yeah, I like this.
Actually-
you should have started with this.
I'm not,
Wait, now it's atomic radius?
that was time radius.
This one is ionization.
Is it off?
No, I think it's good.
Oh, sweet.
That's ionization, ionization energy is opposite of atomic radius. What, Tom?
For the last question, what, are we there? Shall we?
I'm about to do it. Okay. The other one, electron affinity only has a left to right, and then the other one was metallic character, which, more metallic, less, less.
What about the nuclear?
What?
What about the first one, nuclear charge?
We only have that really left to right, and it goes up as you go left to right, which is why the radius gets smaller. What? Yeah. Okay.
The metallic character technically follows the atomic radius.
Yes. All right. Cobalt 3 plus.
Okay.
So electron configuration for cobalt is argon 4s2 3d 1 2 3 4 5 6 7. Okay. When it loses 3 electrons, it loses these 3 first, and then one of those. So it should be Ar 3d6.
Is that a
I just did the whole configuration. Yeah.
Isn't it 3D?
You don't have to do the electronization. What?
I think so.
Oh, hey.
What, Jason?
No.
Okay, Thomas?
So, when cobalt has 3 blocks, it loses 3 electrons.
Right?
So it would have the same number as chromium,
Yes?
but it doesn't have like the same weird
No.
thing as chromium does.
Correct.
Like it does its own.
Right, because the 3D, with that many electrons in it, the 3D actually becomes more stabilized as you put more electrons in it. Okay?
Because you're going the opposite way.
I thought. Okay, this is just like it doesn't really have to do with the test, I don't think.
Okay.
But so if the 3D does fill up before the 4s, right?
Yes. No, 4s fills up first.
Really?
Yeah, really.
Okay.
And
That makes
then-
more sense.
Bromine should be Ar 4s2 3d10 4p6. Okay,
That makes
couple more.
Wait,
So I'll just put it together.
wait. For that one,
I'm not removing the question. What?
the AR3D6,
Uh-huh. The one I just raised, right? What?
yeah.
What?
But you said it was 4.
What?
But you, okay, no, I'm just.
You sure?
Yeah.
Okay. There are only 3 minutes left in class, so we don't have time to go do all of these. But the fourth one, which is bigger, those are the ions, right? So cations are smaller than the neutral atom. So